right? Like, okay, cool. So I wanted to talk about functional equations today. And I expect like some of you do know linear algebra. Is that right? Uh, what is that?
Yes.
Okay. So for the later part of the thing, I'll expect like a bit of linear algebra knowledge, but not really that much. I'll just cover a bit of it. Um, so I wanted to start off with this thing which some of you might know now, but when I was like a few years ago, it was not too common. People just did it. So I want to talk about this thing called pointwise trap, which I don't know where the name came from, but um, I think it's stuck around, and this is what it's called. So um, try the question on the screen right now. Like that's like the most basic example I could give for this question. So uh, try the question. It's pretty straightforward, and let me know what you guys come up with.
Well, f of x can be x or minus x.
Yeah. So where's the solution? So is the solution like one solution this? Oh God, sorry about that. Like, would you say it is one solution this and one solution that?
No, so like just take two sets and like put such that A union B is reals and both are disjoint. So for first set,
Hmm.
f of x is x, and for the other set, x minus x. And
Yeah,
those sets can be anything. There is no condition.
fair enough. Probably not disjoint because you have zero, but pretty much yes. Uh, so yeah, so that's the trap that a lot of people don't really check carefully because like it's very easy to conclude from here that the two solutions could be f of x equal to x, like and one for all x is the point, and f of x equal to minus x for all x. I mean, these two are definitely two solutions, but definitely it's not all of them. As Pranav said, basically, this only means that f of x is equal to plus minus x for all x. So you could have something like this. So that is also a valid solution. And that's basically the trap um, that you shouldn't fall into, that this statement doesn't mean that the only two solutions are f of x equal to x and f of x equal to minus x. Of course, this is one of the more easier examples to work with. So in this case, it's pretty easy to see. But whenever you see something which is like only for one x you solve f of x, it doesn't mean that it follows for everything. Um, okay, so that's the idea of pointwise trap. So there are quite a few ways of like dealing with it. Like in this case, there's no way of dealing with it because the question doesn't give you anything else. But let's say if you would add the condition, like a few conditions into this. So the one I could think of is to add continuity to this question. So what do you think the answer is to this? It's still a pretty straightforward question.
Now it should be x or minus x, right? Like
Okay,
f of
two
x
solutions.
equals to x for all x or minus x for all x.
Hmm.
There's
How would
also
you
a
say?
good solution, I think. F of x equals mod x or minus mod x also works.
Exactly. Yeah.
Because like at zero, you can combine stuff.
Oh, right. Yeah.
Yeah. So yeah, those are the four solutions. Uh, how do you like show that those are the only four though? Like a bit more rigorous. Of course, it is pretty intuitive that like you want to come from here and then you have only like let's say like four ways of going from here. Like it's like, and then you just combine them, something like that. But how do you show that these are the only four solutions? So you have, let's write it down. We are claiming that f of x equal to x.
Like let's say at any other point, like let's say f of x equals to x, like for x greater than 0, it's f of x equals to x till some point a, and
Till
then
some point,
yeah, like till 0 till a, from 0 till a.
I'm not sure about that argument. Um, I mean, how do you find the closest point though?
Okay, I don't
Because
have it with.
let's say if it was like for real rationals, it was at x, and at irrational it was minus x, something like that. Like, then there's no minimum of that set, right? Like, I mean,
Yeah, fine. Okay, that means okay.
yeah, I mean, with reals and everything, it kind of gets messy sometimes to take a minimum of an infinite set. Those kind of things are like something to watch out for.
Suppose let's say f of a. Okay, okay, yeah. So let's say f of a it's positive and f of a plus epsilon it's negative. Like
Okay.
with a positive, let's say similar idea works for
Okay, so there's just some a, so okay, sure. And a minus epsilon, you're saying a plus epsilon or a
a
minus?
plus epsilon.
Okay, cool.
So like it's positive at a and it's negative
All
at
right.
a plus epsilon, let's say. Like, okay,
Yeah.
basically what I'm trying to claim is that if two things have the same sign, like then f of those will also have the same sign.
Hmm.
Uh,
Yeah. There.
so
Yeah.
yeah, I guess
That's about
from
right.
continuity you get that like what do you get?
Oh, something must be 0. Like for some f
Exactly.
of b, that should be
Exactly.
0, which is not possible.
Mm, yeah. Basically, I mean, that's the most. That's the best solution, I think. Like for the sake of contradiction, if you think that for for let's say positives, if there was some a that gives f of a equal to a and some b which is f of b equal to minus b, then from continuity and intermediate value theorem, like you will have some point that would be 0, and you know when it's 0 is only possible at 0. So that's the contradiction. So on either the positive side, it's all positive or all negative, and so in the negative, so you have four solutions. Okay, so that's like one thing, and I'm like continuity is one condition that makes the solution possible. I'm assuming like monotonicity will also, yeah, monotonicity will also make like probably just one solution in that case if it's just all increasing. Um, okay, so these conditions basically are given by like Olympiad problems to make it actually feasible to solve it. Otherwise, I mean, they won't give you like questions which have like pathological solutions basically. But yeah, it's still fun to think about all the solutions. Okay, so um, I hope you guys haven't seen this problem before. I think this is a good example of a pointwise trap where it comes up. Although I did tell you that there's going to be the trap, so you guys know it, but um, try it out. Basics of functional equations. I think probably Evan's handout on his website. Pretty good one. I think yeah.
I got that f of 0 is 0 and f is even.
Okay. F of 0 is 0, and what's the other one?
F is even.
Okay, f is even.
I think the solutions are x square and this minus x
Hmm?
square. I think the solutions are x square and minus x square. I'm not sure about the
Does
minus x square.
does minus x square work?
Oh, I forgot to check that. I think it does. Wait. Oh, wait. Oh, it doesn't. Yeah, it doesn't.
Yeah. It wouldn't have, because there's a f of x here that would mess it up,
Yeah.
because if x square was working, then though, yeah. Yeah, x square is one solution. Is there any other obvious solution that you can think of?
Oh, f of 0 all 0.
Yeah.
Okay, yeah. We take x square plus y equals to f of x minus y. Oh, you're on mute, by the way.
Oh, so you're setting x squared plus y equal to f of x minus y?
Yeah.
Okay. Yeah, good idea.
And then you're just done, except the pointwise part, right?
Mm-hmm. It's not
Like
too obvious. Try it out. It's
the pointwise part.
slight. Yeah, just check it, like when you're doing it. There's some conditions that you need to check.
Oh, okay.
So that's the thing. That's why I give this. You do get two values, yes, but just to be more precise when you're doing this question. Also, if you guys need um, things for like the basics of functional equations, I had written something in high school. You can probably see this. It's really basic, so I think it'll be useful if you want the basics, basically. Okay, so for everyone else who is trying this question, what Pranav basically suggested was try to set x squared plus y equal to f of x minus y. And what that forces is that these two values become equal. And then you can basically say something about this. So that's the idea. And this is a very common trick that you do in a lot of questions, by the way. If you have like two values, which is where you can set these two values to be same.
Okay, I think I'm done with the pointwise also.
So okay, so what did you get after plugging these? What was it?
For like f of x into f of x minus x square is 0.
Yeah, so yeah, for f of x. Yeah, like whatever. So you get the two values, f of x is 0 or x squared. So that's the trap. So what did you plug in? Like, what was the idea with pointwise trap?
So take like some a for which f of a is 0 and put x
Mhm.
equals to a, and then you take
Yeah.
a general y. So you'll get that f of a square plus y equals to f of y for all y.
Okay, so you put like, let's say f of a is equal to 0.
And a is not 0.
And a is not 0, good condition because, yeah. So you put what? A comma anything?
Yeah, y.
Okay.
That will give f of a square plus y equals to f of minus y.
Yeah.
And f was even, so that is equals to f of y.
F was even.
Oh, okay, I'll tell you how it's. Okay, I don't think you need
From,
even though. Yeah, it's fine, you can do it without even. So now if one of them is 0, then other should be 0 also.
yeah.
And if let's say one of them is not 0, let's say like f of minus y is y square,
Mm-hmm. This is
then
y squared.
yeah, then a square plus y I think should also be like squared. Like just assume y is not 0, this is the obvious case.
Yeah, then it
So
has to be a square. Yes. Yeah.
yeah, this will give you y should be equals to minus a square by 2.
Wait. I'm sort of lost. How do you get that?
Like a square plus y squared. So like open the square.
Oh, you just. Oh, from that. Okay, the last part. Okay.
Yeah.
Okay, so you just. Sure. You. Okay, what is the solution to this?
Y equals to minus a square by 2.
Okay.
So like for now, just pick all y which are not minus a square by 2. and you
Okay.
get that f of minus y should be a 0
Mm-hmm.
for all those y. So basically,
Yeah.
except for y equals to minus a square by 2, it's 0 everywhere. So now just
Mm-hmm.
pick any other a instead of this a, like pick some b which is not equal to a. Then for y equals to minus a square by 2, that's again 0. So it's 0
Yeah.
everywhere.
Yeah. Good job. Yeah, so that's basically the idea that you have to be careful about the minus a square by 2 part, but I think, yeah, basically. Uh, Usually what I tend to do with these questions is a slightly different way, which is basically the same idea. It's just a different way of doing it, writing it out, which is to think like, let's just, because I think that that thing is quite general to solve in like most questions. So like define like a set, let's say, which is like a such that f of a is 0, and let's say b with f of b is 0. F of b is b square. And let's just assume that, let's just take like, uh, I think the idea is to just try and put like a comma b or like b comma a, those kind of things. And I think in this case, if you just put like a comma minus b, when you put it, I think you end up getting something like, I think which is what Pranav got was basically you'd get that a square has to be 2b. And then you can basically force that. You can basically find two values from a and b that do not satisfy that. So yeah, so it's basically the same idea. It's just a different way of writing it out. So yeah, so that's basically how you deal with pointwise trap, like a couple of ways. Like either they would give you like a extra condition like continuity or monotonicity, blah blah blah, or you need to use the original question and then it's basically use a contradiction, like assume that there are two values and then you basically put them back and then you'll get a contradiction somewhere. So that's the trap. That's the first part of the lecture that I wanted to talk about. The second part is, okay, didn't need the slide. Okay, so the second part is to solve the functional equation. The first form, like the basic one. So what is the solution that we know? Like what kind of properties do we already know about this function?
It's like linear if it's continuous or bounded,
Okay.
or there is
Without
already.
that, let's assume without that, what do we know already?
Mhm. It's additive.
Like what values do we know? Like it takes at some certain
Oh, f
nice
of 0
ones.
is 0.
Okay,
We
cool.
also need that rationals. So like f
Oh,
of
right.
q is qf of 1 for all rational
Yeah.
scale.
Yep. And I think you can pretty much show that. I think fq like some alpha is also qf of alpha. I think that's also fine, right? I guess.
Yeah.
Yeah, so it's the same thing. Uh, but I think that's basically everything that we would get from this, just that much. So usually what they do, like Pranav mentioned, was like they would give something else. So if you do continuous again, so like your rationals are something like this, like it's not like that, but and if your irrational takes something else, but if it was continuous, then you'll basically mean that has to be linear or everywhere. Um, so I think I didn't know. Okay, so I think these are the few conditions that we know that I wouldn't go through because I'm assuming we all know these. So if they give an extra condition, then we know the solution that's linear. Okay, so I just wanted to talk about like what the general solution would look like. And it's basically how much the information we already know is enough to basically write a general solution. So what we know is Q alpha is Q f of alpha for okay, so I'm assuming we know a bit of linear algebra. So we have a vector space, the reals. So we have R. And like the operation that we're doing right now is something based on linear. So we want like a Q vector space, which means that our scalar values in the vector space. So your vector space is such that is a thing which is like you can do addition in that or scalar multiplication. And if it is a Q vector space, I'm telling that lambda has to be in rationals basically. So in that sort of vector space, let's just assume that we can find a basis. The proof for why there is a basis of R as a Q vector space is, I mean, there's a way of doing it using axiom of choice and everything. But let's just assume that there is a basis. So let's just say that R has a basis of, how is it? So let's just say the basis is like set of values which are, and I think we can try and prove that this set is uncountable, but I'll leave it up to you guys. So that's why I am not writing it as E1, E2, dot, 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 because it's an uncountable basis. So it's kind of hard to think what's happening here, but let's just go through like what certain values could be. So we know
R
that
is
the
like,
R is the
the-
reals.
okay.
R is your reals, and you want a basis using only rational vector space, basically. So let's say like if you want to come up with root 2, there's no possible way of writing root 2 as like rational values or like a bunch of irrationals that add up to that. So you would need root 2 as a basis. Like in one basis, it could be a root 2. Then you would also need root 3. Then you will also need pi, all those things. So in very vague sense, let's just say that what you could do is like you can cover up until one point and then you can add another real value that was not already covered. But in the vague sense, but that will lead to a countable set, but this basis is an uncountable one. So basically what we're saying is that you can express, you can express every real, let's say x, as a unique combination of, let's say, A1 So you can express every real as a linear combination of your bases, your vectors and your bases, and where all of these values are rational. So this is an assumption I'm taking because the proof for it is a different thing. If you want to read, I can. You can read about Hamel basis. So I'll just put on the chat. You can read about this, but yeah, basically it's that's the linear algebra part of stuff which is not very obvious as well. But yeah, so if we have something like this, let's just assume that we have something like this for now. Then we do know what f of x would be, right? So if you assign a value to each of these things under f, then let's just say this is like what do you call it? F.
These E alpha belong to Q, right?
A1s are rationals. Your other values are not. They're just some reals that create the basis. So how do I say a basis? Basis is basically that can span the entire vector space, and they are linearly independent. So if you have linear independence, basically means that if you have something like this equal to 0, then that would have to mean all of these values are 0. So you cannot express one vector as the sum of the previous vectors. And spanning means that you can express every vector in the vector space that you need in terms of your basis vectors. So that's the basis. So we are assuming that this is the basis, and in a Q vector space, all the scalar values are rational. So all a1, a2, an are rationals. So think of it like if you assign every basis value, like let's just say it was root 2, root 3, root 5, like they're nice values. And we assign some value to root 2 under f, some to root 3. Then we can express, let's say, all reals in terms of these values and then as a linear sum. So we know what f of x would be, right? So let me just put it like this. So suppose that if we had like f of root 2 is like 5 and f of 1 is 1, there would be no contradiction in these two statements. Is that all right?
Yeah.
And similarly for let's say like f of root 3 and something, anything, f of pi can be anything. And any linear combination of these values would basically give you some f of x equal to, you can eventually find it out, like the value from these. And the point is that because we knew that there's a basis like that exists, so any x can be expressed as the sum of them. So if we only assign the values to the basis, then we can find what f of x is. So that's the general solution of this thing, which is, I mean, it's not the nicest thing, but I mean, in some better cases, there would be nicer solutions. So let's just think like how do you plot it out? Let's say like you might have something like for rationals, it's like this. I mean, then let's say for root 2, it went like, for some other value, it went, I don't know. And these are all like dense values as well. So yeah, that's the general solution of functional equation, this additive one. And if you add like your general conditions now, like continuity, monotonicity, now you see why each of those things basically end up giving you only the linear solution. The idea being in that case is that you can show that if they're not, then it will basically be a dense set of all these values going like that. So R square would be, these values would cover a dense set in R square, and then that would not be possible if it's continuous and everything. Okay. So let's try this question with you have the additive part of it and an extra condition.
But like the main idea is that basis which you had, you can like keep on pairing things up. Like let's say you pair E alpha 1, E alpha 2. Okay, I'm not sure how do you pair in uncountable sets, but like let's say if it was
Okay.
count, yeah. Then you can
Yeah.
like
Yeah.
pair two things. Then f of E1 is E2 and f of E2 must be E1.
Mm-hmm.
And you can just keep on doing this and then that will form the solution.
That's a good idea.
Because like also in that basis, like nothing can be this rational.
Yeah. Um, I think the problem with that might be the countable part of it. I think that's the only issue.
Yeah.
But yeah, for a finite thing, I think that would definitely work. I think what we can do is that instead of like pairing up things that we do not know how big that set is, we could do something like for each value that we know, we were assigning like E alpha. Um, we were assigning E alpha to something, right? In like the wake sense. So if you assign it to like, let's say like plus or minus one, then that will also work, right?
Wait,
Yeah.
can you repeat that?
So if you just assign like, sorry, um, so if you assign each E alpha to plus or minus E alpha, basically. So either basically I'm saying X or minus X as the two values that it's taking. And in that case, it will basically work, the involution.
Yeah.
Right. It turns out that, I mean, those are not the two only solution, but it pretty much is like what the values are only will take basically. And let's try and show that okay, let's just say that there's a set A which takes f of, sorry, which is x such that f of x is x and b is such that okay. Can we express some value, any real value? Okay, I'll give you the task to do basically. Try and express any x as some a plus b, where a is an a and b is an b. Try and find some a and b that satisfy this.
What are we supposed to do? Like A and B are two sets given to us, right? Which follow this.
Yeah. I mean, like this is like, let's say like two sets exist. Like I mean, they would exist like some values. Then try and show that you can express any real as a sum of
Okay.
two values a plus b.
Okay. So maybe consider like A to be some epsilon, for which f of epsilon is epsilon. Okay, that's just epsilon is bad. You don't need epsilon. Let A be something which for which f of A is A, and
Yeah.
then you take B minus A. So if f of x minus A, if f of x minus A is x minus A, then that is good. Oh, B must be capital B. Can't we have
Yeah.
like A and B both in A? Like,
That's not what we want right now. Just
okay.
try. I mean, like, yeah, there's a reason why I asked you to do it, because that's like how the general solution follows from this. So
Okay.
just try and. I mean, you can come up with A and B is the point. It's not. It's kind of tricky, but it's not too hard. You can basically come up with the exact values that would work.
It's like x plus f of x by 2 and x minus f of x by
Yeah, yeah, that works. So you can see that that's a good solution, by the way. So if you put x plus f of x, so f of that would be f of x plus f of x, which would again be f of x plus x, and f of x minus f of x is the negative of that. F of x minus x. And you can always scale these things, so that's fine. So if you put, so this value is in A and this is in B. So any x can be expressed as A plus B, where A is in A and B is in B. Okay. And clearly, like A intersection B is 0. Okay. So you have this, then what is f of x from that in terms of A and B?
a minus b.
Yep. So this is actually the general solution that works basically. So to summarize, what we had was, if you have any two spaces that A and B that generate R, so you have A plus B to R, and is only 0, then you can basically do f of A plus B, set it to A minus B, and the point is that because it generates all reals, you can express any x in terms of A plus B and set that to A minus B. And that actually is the general solution to this question. So yeah, I hope that makes sense.
Can you repeat what's the solution? Like, I got A plus B equals to R and A intersection B 0. But what do you do after that?
I was thinking of two sets that actually do this. But okay, basically, let's say that root 2 was in set A and root 3 was in B. What you're drawing is that you're setting f of like any linear combination of root 2 and root 3, like f of root 2 plus root 3, you set it to root 2 minus root 3. So the point is that because you can generate any real as a sum of A plus B, you set f of A plus B as A minus B. And that's the solution. So if there is a solution, then there exists AB with these properties. And then you can basically set x as A plus B and f of that to be A minus B. And I mean, in all of these conditions actually can be written like R is equal to direct sum of A and B. But that's like the vector linear algebra way of writing it out. So direct sum is basically, it is a unique combination of those two, and you can express any value as a sum. Do you guys see why it is unique, by the way? Why x, we showed that x can be expressed as A plus B, but why were A and B unique? Or we didn't mention it in the previous slide. So we did show that x is equal to a plus b, but why were those a and b unique?
From the two equations, you just get a is x plus fx by 2.
Sorry?
From the two equations, you just
Yeah.
get a is x plus fx by 2.
Yeah, but that doesn't mean that it cannot be expressed as any other way, right? I mean, we know that x plus f of x divided by 2 is in set A, but I mean, it could have been possible that there was some other value in A that we do not know the form of, and it's something in B that added up to x. From that equation, yes, that was the only solution, but why was there no other solution?
Right. Yeah.
And that is important. Otherwise, a function that we define in the next slide wouldn't be well defined, because we are saying that you can express x as a plus b, and then you set it to a minus b. But what if that a and b weren't unique? Then we kind of getting it wouldn't work out basically.
This is like, I'm not even sure if this works, but like, let's say x is equals to like a plus b and c plus d.
Okay. Can we take a1 b1 something to remember, like
Oh yeah.
so that we
A1,
know that
B1.
it is an a. So okay, a1 b1, and let's just say a2 plus b2.
Oh, I just assume. Oh no, that's true. Yeah. So a1 minus b1 equals to a2 minus b2.
Yeah. A1 minus a2 you mean, or
a1 minus
b2?
b1.
Okay. A1 minus b1.
Yeah, because like take f of x. So f of x will be equals to f of a1 plus f of b1, and f of a1 is a1 and b1 is minus b1.
I mean, we were not going that far. I just meant like without the f part, like without doing f of something, because right now we haven't said the. Let's just forget that we know the solution. Is
No,
that
that's
I'm
not the
just trying.
solution, right? Like, because we are representing x as a plus b, and then this thing is equal
Okay.
using that f of x plus y equals to f of x plus f of y condition. So like
Okay.
f of,
Sorry. Yeah. Okay. You take f of. Okay. Sorry. I messed up. So you're taking f of that,
yeah,
and
and then
that's
f, yeah,
okay.
and that is also equals to a2 minus b2,
Mm-hmm.
and then you can just add like a1 plus b1 equals a2 plus b2, and a1 minus
Okay.
b1 equals. So that will give
Yeah.
a1 equals a.
Fair enough. That that definitely works. I do not think that we need to do that much as well. So let's just say that you could express a1 plus a1, a2 plus b2. I think the point is that any two values in any sum of values in a would give a value in a basically. So the point is that this is a Q vector space. Does that make sense? So if you had f of x equal to x and let sum f of y equal to y, then your sum would also be f of x plus y is x plus y. So if two values are in A, their sum is in A as well. And if you do a rational scaling of it, then it will again be in A. So both of these are like Q vector spaces. Okay. And your point is that A1 minus A2 is B2 minus B1, right? This is in A because linear combination of two values in A remain in A, and this is in B, but we know that A intersection B is 0. So this has to be 0. I like this method more because you would come up with this and when you're doing linear algebra. So there are these properties of vector spaces in general. So just write it out. So if you had something like V as U plus W and V as we have, sorry, and the intersection is 0, then that's called a direct sum, because you can express V as a unique sum of U and W. So you write that as, right, for all V, you can express V as U plus W, and these are unique values, unique representation. So that's the point, that in the previous problem, you didn't need to have f of that additive condition in general. You just need to know that A was a vector space, B is a vector space, and the intersection was 0. So it would be a unique representation. I hope that makes sense, because I'm assuming you guys haven't covered a lot of linear algebra, but I hope this still makes a bit of sense.
Yeah.
Yeah,
Okay,
got it.
cool.
I
Yeah.
have one
So
doubt.
yeah.
This f of x equals to a minus b solution thing is not the set of all solutions with the condition, right?
It is all the solutions,
Oh,
because
but
because literally what we did was, like, we assume that we're assuming that there's a solution, right? Like f is a solution, and then what we do is, like, we define a and b. Like we can define a and b, right? Like if you were given a general solution to this thing,
yeah,
a and b, and then we basically did show that f of x can be expressed as a sum of a plus b, and
yeah.
implies that f of x would be a minus b. So any general solution is of this form, and any solution of this form is a valid solution.
Okay, like, but how about, let's say we take root 2 and root 3, and we say f of root 2 is root 3, and f of root 3 is root 2. And apart from root 2, root 3, we fill in the values in a and b. That will give us another set of solution, right? Except I'm not sure if that will still satisfy the linear condition.
I do not think it will. I think there would be some issue with the when you're trying express it out in a linear form. I think it would break somewhere.
Okay,
I think that's it. Yeah, I think the swapping thing works with involutions generally, but probably the additive will make it break. I think that's the thing.
Okay.
Yeah. I think the idea would be more complicated, because you might end up with, let's say, again with some a and b, and then root 2 would be expressed as some sum of, or maybe like that could be a solution expressed in this form. I mean, it could really be, I think it could be valid actually. Like uh if the set A would have, if root 2 was expressed as, I don't know, some a plus b, where a minus b ended up being root 3, and root 3 was expressed as some a1 b1, and a1 minus b1 became root 2. I think your solution might be true as well. Not
Okay.
complete.
Makes sense. Yeah, I think
Yeah.
we cannot like find the explicit values, but like general.
Yeah. I think I mean, that idea should work as well. I think so. Not sure, but because I think in like all of these cases, like there's always the idea of pathological solutions being a bit beyond our understanding because of the uncountable and everything. But I think what you can think is that you can generate any solution using this form. So if like just to summarize, if you write R as some A direct sum with B, if you can break it down into like rational vector spaces of A and B, and you express at any f of x as A plus B and set it to A minus B. So that is your general solution. I hope that sort of makes sense. Okay, let's try this question, which turns out to be similar to the previous one in some ways.
Okay, so if you take x as 0, then you get f of y is y plus f of 1. And you take y as f of y, then you'll get f of x plus y plus f of 1 is y plus f of x plus 1. And you can take
Okay.
x to be x minus 1 then. So you'll essentially get x plus y is f of y plus f of, okay, there are some, yeah. So now you take x as x minus 1, then it's f of x plus y plus f of 1 minus 1
You're taking
equals,
x as x minus 1. Okay.
yeah,
Okay.
equals to f of x plus f of y.
Sure.
So like it somewhat resembles that.
Sort of.
Cauchy.
Yes. So I think what you could try is to do
Oh,
some substitution to get it there.
oh, I think you can do like g of x is f of x minus x, where uh no, not x, like some constant in terms of f of 1 minus 1.
Yeah. Think of that. Try and reduce this to. You can see like it is coming there, but just find the exact substitution that would basically get you there.
Okay. like f of x minus x equals g of x would give g of x plus g of y is g of x plus y plus g plus g1. But that still doesn't look nice enough.
I think try and get rid of the 1 minus f of 1 part of it, if there's a way.
I think like the usual idea is you take like let's say that is c, so you take minus 2c both sides, and then f of y minus you can pair and f of x minus you can pair. But then you'll have a constant left on the LHS.
Mm-hmm.
Yeah.
I mean, if you're putting something like instead of here, like some x plus c or something, then you get some y plus c kind of thing. You'd get plus c out here, plus c from outside here as well. That would cancel out. So that should be fine, but I mean, so what I'm trying to say is that if you change it by a constant, then it wouldn't be that bad. So you can add like plus c. That the outer plus c would get cancelled. So the only thing remaining would be the thing that you get from f of x plus f of y plus some c or something. Basically something like that is what I'm saying. And the remaining would be the similar part.
Oh, right. So we can remove f of 1 minus 1, right? That way.
Mm-hmm. So
Like
what
you're
yeah.
essentially saying that if you like take g of x as f of x minus x, then from the original condition, you'll have
g of x is f of x minus x.
oh not x, f of x minus c, some constant.
Sure.
Uh
Okay, let's just do it together. So good. Okay, so you're putting f of x as that, so you get I'll be slow with this. G of x, g of y, the c. Let's get g here. That's fine. And
What
some
if
y.
it is like injective or something like that, or surjective? We can
I think you can show both. I think you can show both of them. It's not hard. I think it is bijective.
Okay, then we can like do things because f is bijective.
Yeah. That is one way of doing it. You can try that as well. But I mean, we were just trying to get the form a bit nicer in just the thing like x plus 1 wasn't looking too nice. We were trying to get it to get it look a bit better, basically. So I think from here we get a nicer form. Pranav. Like if you set
Yeah.
x as -1, so you get what? Right?
Yeah.
If I'm not wrong, this is what you get. And then you can set c as 1, basically.
F of 1, right? Oh, okay. Up there, yeah.
Yeah.
Yeah, right.
I think this is what you should get, if I'm not wrong.
Yeah.
Mhm.
And
So
then
we
you can
have
also get g of x plus y as g of x plus g of y using the same idea.
okay. We have I'll just write it down. So this is the new equation that we're solving for. And we will also get similarly g of x plus y is g of x plus g of y. What else? From using these two facts, basically. What do we get? Implies.
You get G is involution.
Yeah, exactly. Just put here, so you get g of x plus g of y. So you basically end up getting the same two conditions, that it's additive and involutive. And you know the solution to that, so you basically get the solution to f. And that's basically the general solution to this as well. Uh, so yeah, that was the question. With the case with the person saying about bijective, I think usually on most problems, that's the way of doing it. I think it's just that this problem gave you pathological solutions that a general problem wouldn't have. So bijective is usually the way of proceeding with most functional equations, though. And it could have been possible that we would have needed it somewhere to cancel out some stuff, but we didn't need it. Okay, so we have
What is the
just
source, by the way? Is it some college contest?
this is according to the one I have written on mine, it is some Albanian TST problem. I do not know the year. If you
It's a
can,
Olympiad problem? That is
I
interesting.
think some TST problem. This is what my source is saying, but I don't know if I am not I haven't verified that, but I think
Okay.
it might be true. Some random TST problem basically. It's unlikely though to ever get a question that has pathological solutions.
Mhm.
Probably improbable, like completely improbable. Okay, this was basically what I expected the class would end, and I had these many questions, and I thought that. So in the meanwhile, while you guys were doing the problem, I found another one that we could do in the last 15 minutes. I think this is slightly harder.
Well, for rational, it's like f of x is x or minus x, and we can
Mhm.
or zero as well, and we can rule out the minus x case because if f is a solution, then so is minus f.
Yeah, mm, that's a good idea. Yeah. So you're saying the three solutions are x. And if f is a solution, then minus f is also a solution. Yeah.
Okay, also in that previous thing where we did
Mhm.
f is involution and f is linear,
Mhm.
how do you really motivate taking the sets A and B, that like assigning basically f of E alpha as plus minus E alpha?
I think the point was that you had to get f of x back to x, and with such uncountable sets, I think the point is that you want to use the same value to get back to that. So in the previous one, we were defining f of e alpha to be c alpha, like
Uh-huh.
ce alpha, sorry. In that case, you basically involution forces the value of c to plus or minus 1 is the point. So you
Okay.
kind of guess that plus or minus x is the ones that are working, and then you come up with this. And I think in the like this idea in general is hard to like this is hard to get an intuition about these things. So
Uh,
hmm yeah, that's a good idea. What would that give you? That's a pretty good idea. Yeah, in some ways, I think just trying to compare the coefficients, I think you're pretty much there. Like, try and think about how many solutions that it's like a polynomial there. If you think about it in Q, like you can take out Q and then you get a polynomial, and then how many solutions does that have? What does that tell you? I mean, you already have Cauchy though. You already know it's additive, but and yeah, I think I'll be nice and tell you that these are the only three solutions. By the way, okay.
all right, so you get something like f of x plus q times f of 1 to the power 2013 is equals
Mm-hmm.
to f of x plus q power 2013. Like the power is
Yeah.
inside. And
Yes.
then when you open this power, you can like take the individual f's. And you
Yes.
basically just have to show that there exists some power for which the coefficients are not equal, except like the power 0, like the rightmost one. And if you
Um.
show
Yeah.
that, then it's basically a polynomial in f of x, and it satisfies for all q's. So there are infinite roots.
Yep. So
So
it's strictly equal is what we would
yeah.
get. Try and get a bit more mathematical with it. Like that's the idea basically. That's
Mhm.
yeah.
Okay, so I think it's something like some rational coefficients, and then you have f of x into 2012, like it's essentially 2013 q into f of x to the power 2012 into f of 1 minus f of x power 2012. This is like the first term. And then you
Yeah.
can keep on doing this, like 2013 choose to and stuff you'll get. And this is like 0 for all x. Oh, but f might not be polynomial.
I mean, f is not a polynomial, but we get. I mean, not necessarily even, but I think even the next power which should work, right? I think what you should be getting is something like. I think this should be true though. Okay.
Yeah, something like this only I'm getting. But like, how do you show that these are equal? Like, fine, you have some rational coefficient multiplied by like minus this term equals to 0. But why this?
I mean, what you're getting is that this would be true, like the two polynomials when you compare the coefficient. These are the coefficients, right? And it will be true for all rationals, right? I mean, the whole thing is a polynomial in Q.
Oh, whole thing is okay, fine. Yeah. I was
The
thinking
entire
whole
thing is
thing
a
is,
polynomial.
yeah.
No. Take the polynomial in Q, basically. Everything is in Q. And then
Yeah.
you X and Y as X and 1 in this case. I mean, you could have done it for a general Y as well, by the way, which would have given you the similar thing. So you can change Q. Q is the variable, and then it's true for all rationals. So that would mean the coefficients are equal.
Yeah. Okay, I was thinking polynomial in f of x. I don't even know why I was thinking.
Yeah, then you're trying to solve. Yeah.
That was just weird.
No, that's fine. I mean, yeah, but basically you get this, and what do we get from you? I'll just be nice and just tell you guys that I think it's going to be true in a bit more general case, which I think would be helpful. So if you solve the equation that I wrote above, instead of using x and 1, you can use x and y and get the same thing basically. For k equal to 0 to 2030. I think rather your equation with 1 might be more than enough as well. So what is f of 1, by the way?
It's like they have 2013 possibilities, no? Like any root of 2013.
We are working with reals.
Oh, 1. Yes.
Okay. Right. Yeah, that works. I think what you could also argue is that f of 1 is either 0 or 1, right? So if it was 0, this equation forces all f of, you can basically take x to be like, I don't know, 2 or something, and then pick 1, I guess. And it basically forces it to be 0 everywhere. And if f of 1 is not 0, so it is 1, so you get something like this. And that would mean that it is positive for on the real axis as well. So f of x squared is is f of x squared. So on the real axis, it is bounded again. So basically, you get that additive conditions for Cauchy and the nice ones, and then you basically get linear and 3 solutions. Okay, I think it's an Elmo problem. Not a problem, but Elmo shortlist. So might be famous. Yeah, I like the question. Okay, so I think that's all for this. I hope you guys learned something new, hopefully. And hopefully it was understandable to everyone. Are there any questions before we wrap it up?
Should I stop recording?
Yeah, sure.